The chemical signatures we are observing around the interstellar comet 3I/Atlas offer a rare and compelling glimpse into both its ancient origins and the extraordinary journey it has undertaken through interstellar space before entering our solar system. This object, only the third confirmed interstellar visitor ever detected, represents a scientific opportunity unlike almost anything previously available to astronomers. Detected on July 1, 2025, by the Asteroid Terrestrial Impact Last Alert System Atlas, 3I/Atlas was identified far earlier in its solar approach than past interstellar objects, such as 1I/Oumuamua and 2I/Borisov. That early detection has proven crucial, allowing scientists to observe the gradual chemical awakening of an interstellar comet as it responds to increasing solar radiation. Interstellar objects are invaluable precisely because they preserve chemical and physical information from star systems far beyond our own, effectively acting as cosmic messengers, carrying material formed billions of years ago in environments we may never directly explore. Each molecule and atom released from such a body offers clues about the conditions under which planets and smaller bodies form around other stars, making 3I/Atlas a true time capsule from another planetary system. For an international research team using the European Southern Observatory's Very Large Telescope (VLT) in Chile, this comet presented an unprecedented chance to track the chemical evolution of an ancient object in real time. Observations were conducted using two highly sensitive spectrographs, X-Shooter and UVS, both capable of dissecting faint cometary light into its component wavelengths. These instruments allowed the team to identify specific atomic and molecular signatures in the comet's tenuous atmosphere, or coma, as it slowly warmed during its inward journey. Early spectral data suggested that 3I/Atlas formed billions of years ago, potentially predating the formation of our own solar system. If this is the case, then the materials released from the comet are not merely foreign in origin, but also represent an earlier chapter in cosmic history, providing insight into how solid bodies formed in the early Milky Way. The most surprising and scientifically intriguing result came with the detection of glowing atomic nickel vapor surrounding the comet at a distance from the Sun, where such behavior was thought to be impossible. On July 20th, when the comet was still nearly 3.9 astronomical units from the Sun, almost 4 times the Earth's sun distance, spectral lines consistent with neutral nickel, NiI, were detected. At these distances, temperatures are extremely low, far below the point where metals like nickel would normally vaporize through simple heating. Yet the data showed unmistakable emission lines, indicating that nickel atoms were being released into the coma. This phenomenon had previously been observed in some solar system comets, but always much closer to the Sun, where intense heating could plausibly explain the presence of metallic vapors. Seeing this effect so far out-challenged existing models of cometary chemistry and suggested that an entirely different mechanism might be responsible. As observations continued, the nickel emission grew steadily stronger as 3I/Atlas moved inward. Over multiple observing sessions with the VLT, spanning late July and early August, the increasing intensity of nickel spectral lines painted a picture of progressive chemical activation. Rather than a sudden outburst, the release of nickel appeared to be a gradual process, closely tied to the comet's changing environment. This trend was documented in detail through continuum-subtracted ultraviolet and blue spectra, revealing a dense forest of nickel emission lines across a wide wavelength range. The strengthening of these emissions over time suggested that whatever process was liberating nickel atoms became more efficient as solar radiation increased, even though temperatures remained far below those required for conventional metal sublimation. The presence of nickel at such distances raises profound questions about the physical and chemical nature of interstellar cometary material. One possibility is that nickel is not present as pure metal, but instead bound within complex organic or mineral compounds that can break apart under relatively mild solar irradiation. Another hypothesis involves photochemical processes, in which ultraviolet sunlight directly breaks chemical bonds, freeing individual atoms without the need for high temperatures. These mechanisms would imply that the comet's composition is fundamentally different from that of typical solar system comets, or at least that it preserves more pristine materials that have not been extensively altered by repeated close passages to a star. Because 3I/Atlas has likely spent most of its existence drifting through the cold vacuum of interstellar space, its materials may retain chemical structures rarely seen in objects that formed and evolved within our own planetary neighborhood. By mid-August, as the comet reached a distance of about 3.07 AU from the Sun, another familiar chemical signature emerged. The team detected cyanogen, CN, a molecule commonly observed in solar system comets and often used as a tracer of cometary activity. The appearance of CN marked a new phase in the comet's evolution, indicating that more volatile compounds were beginning to sublimate or dissociate as solar heating increased. The sequence of chemical activation, first nickel, then CN, was particularly intriguing. In most solar system comets, CN is detected relatively early, while metallic emissions typically appear closer to the Sun. The reversed order observed in 3I/Atlas suggests that its chemical inventory, structure, or surface processing history may differ substantially from that of comets formed around our Sun. This evolving chemical picture reinforces the idea that interstellar comets are not simply copies of familiar solar system objects formed elsewhere. Instead, they may represent a broader diversity of planetary building blocks, shaped by different stellar environments, radiation fields, and chemical reservoirs. The detection of both nickel and cyanogen provides valuable constraints on theoretical models of comet formation and evolution beyond our solar system. It also highlights the importance of early detection and continuous monitoring. Because 3I/Atlas was spotted relatively far from the Sun, astronomers were able to observe the onset of activity from its earliest stages, something that was not possible with earlier interstellar visitors. Beyond the specific chemical findings, the discovery of 3I/Atlas marks a turning point in astrophysics. With improved survey capabilities and more sensitive instruments, astronomers are now entering an era in which interstellar objects may be detected more frequently and studied in far greater detail. Each new detection has the potential to expand our understanding of how planetary systems form and evolve across the galaxy. Interstellar comets, in particular, offer a unique window into the solid materials that exist around other stars, complementing observations of exoplanet atmospheres and protoplanetary disks. They allow scientists to study real, tangible samples of extrasolar material without the need for interstellar travel. In this broader context, the glowing nickel vapor around 3I/Atlas is more than a curious anomaly. It is a signal that our assumptions about cometary chemistry may be incomplete and that the universe continues to surprise us when we observe it closely enough. The chemical signatures seen in this comet likely reflect both its ancient formation in a distant star system and the transformative effects of its long, lonely journey through interstellar space. As it continues its passage through our solar system, 3I/Atlas will remain under intense scrutiny, offering new data with each observation. In doing so, it reminds us that even small, icy bodies can carry profound stories about the history of the cosmos, bridging the vast distances between stars and bringing pieces of other worlds into our scientific reach.